Good morning, Algebra 2. We're about to begin Unit 2 Notes, Day 5. Now, you might want to pause the video and write down what I currently have on my screen, or just simply observe. We have, in some ways, already covered this material. Now, if you'll notice the black absolute value right here, that function here, notice the vertex is at the origin. Then look at what happens when they add a +1 to the right of the absolute value. That's the graph in red. Notice it shifts up from the origin. Then notice what happens when they put -4 to the right of the absolute value. It shifts down 4. So yeah, any numbers that are to the right of the absolute value, outside of the absolute value, are going to be your shifts up or down most of the time, unless they rearrange the order. But when we get there, I'll point that out. Now, if you'll notice here, we have the parent function of absolute value. Once again, that's the one in black. Now look at the x minus 2 that is inside the absolute value. That means your graph is going to shift right or left, and it's opposite of what you think it would be. So yes, it's x minus 2, but that means it's actually going right 2 units from the origin. Here we have x plus 5. Notice that the graph in blue shifts left 5 units. Moving on. Here we have our parent function, the graph in black. When you put a 1/2 in front of that absolute value, that is known as a shrink of 1/2. Look what it does. It's the one in red here. A shrink can also be called a compression. Just a heads up. The number in front here is 2 this time. That's going to be our graph in blue. That's called a stretch of 2. So just notice the differences there. And then over here, we have our absolute value in black, the parent function. If you put a negative in front of that, though, it's going to flip it upside down. That is known as a reflection over the x-axis. That's a lot to write down, so I abbreviated. And then here, if there's a -2, well, we know it's going to flip it upside down. We just covered that. And since it's a stretch of 2, look at what it does to that graph. Anyway, that's another reminder of transformations. And then if we look down at our paper here, they've given us some equations, and we just have to list what is going to happen to the graph. So if we have that +3 to the right outside of the absolute value, that means our graph is going to go up 3 from the origin. Here we're going down 3. Here, now we have x plus 3 inside the absolute value. We're going left 3. Here we have x minus 3 inside the absolute value. We're going right 3. Here we have a 3 in front of our absolute value. If your number in front of the absolute value is bigger than 1, then it's a stretch. If it's in between 0 and 1, then it's a shrink or a compression. Here we have a negative in front of our absolute value. That is a reflection over the x-axis. Your graph is going to be upside down, like that. Move on to side 2. Here, vertex form of absolute value equation. This is the formula of absolute value in vertex form. And I will make sure and explain all of this information as we start doing some math problems. Here for this section, name the transformation of each graph from the parent function f of x is equal to the absolute value of x. All right, so from left to right, notice the negative in front of the absolute value. If you'll remember, that is a reflection over the x-axis. Here inside the absolute value, I see x minus 7. That means this graph must be shifting right 7. Now, in order to identify your vertex, here's what you're looking for. You're looking for any horizontal shift here and any vertical shift there, more times than not. Here, we went right 7. That's the first number of our vertex, positive 7. Here, there is not a number at all, so just put 0, and that is your vertex. All right, example 2 here. Notice the 3 in front of the absolute value, since that is greater than 1. That's going to be a stretch of 3. I'm going to abbreviate stretch of 3. Inside that absolute value, I see x plus 2. So we must be going left 2 and out here to the right. That's a minus 10, so we're going down 10 from the origin. Our vertex, remember, we're looking here, we're looking here. Or you can just use these numbers that we just wrote down, can't you? Either one will work. Now, since we're going left 2, do negative 2, down 10, minus 10. That's your vertex. Here, we have a negative in front. That's a reflection over the x-axis. Now we have 2/3. It's not negative 2/3, it's just 2/3. That's the way I want you to look at that. That number is in between 0 and 1. Therefore, we have a shrink or a compression. It means the same thing, but I don't know what term they're going to use. We have a shrink of 2/3. Looking inside the absolute value, looks like we're going left 6 and to the right of the absolute value. Down 7. Left 6, down 7. That's our vertex. Left 6, down 7. Okay, looking here, we have a 6 in front of the absolute value, so that's a stretch of 6 inside the absolute value, x minus 1, so right 1. And we're not going up or down any from the origin. So our vertex is right 1, and we didn't go up or down any, so 1 comma 0. We have a 2/3 in front of this absolute value, so that's a shrink of 2/3. Nothing inside the absolute value other than that x, so we're not moving left or right from the origin. And then plus 4 to the right of the absolute value. So up 4. Our vertex, if you look inside the absolute value, notice it's just x. So let's put a 0 here. And then to the right of the absolute value, positive 4. All right, example 6. Example 6. Looking inside the absolute value, looks like we're going right 5 and then up 4. And guess what? That's our vertex. Right 5, so positive 5, up 4, so positive 4. Now down here, write an absolute value equation given the following transformations. Moves the graph right 1 unit and down 4 units. Start with y equals. Open your absolute value. And then x, since it's going right 1, do minus 1 inside of that absolute value. And then down 4 units. Like that. Here reflects y across the x-axis, moves it right 3 units and up 2 units. So y equals a reflection across the x-axis. So put a negative in front of your absolute value. Moves to the right 3 units, minus 3. And up 2 units, plus 2. Here has a vertical compression of the graph by a factor of 1/4 and moves left 8 units. That compression of 1/4 means put a 1/4 in front of your absolute value. And then it moves left 8 units. So plus 8 inside the absolute value. Here, it moves the graph left 1 unit, down 5 units, and vertical stretches by a factor of 3. Vertical stretches by a factor of 3. We're going to start there first. Moves the graph left 1 unit, so x plus 1 in the absolute value, and then down 5 units. All right, move over to side 3. Okay, on side 3 here, we're going to write an absolute value equation for each vertex, assuming that a equals 1. So what that means is there's no stretch, there's no compression. So just start with y equals. That very first value is going to go inside the absolute value. And since it's -6, we want to do +6. And then that value goes to the right of the absolute value. Okay, here it's +3. The very first number is +3. So in the absolute value, do x -3. And then that last number is -4. Here, our first number is 0. So what that means is you actually don't need anything inside the absolute value other than x. And then the second number is +15, so +15. Okay, here we're going to write the equation for each graph. Now, we can tell that since its vertex is at the origin, we're not going to have anything inside the absolute value other than x and nothing to the right. But we do have either a stretch or compression going on here. What I want you to incorporate is rise over run. So here's a perfect coordinate, and of course the origin was a perfect coordinate. In order to get from this dot to that dot, we'd have to go up 3, right 1. Up 3, right 1. So we have a stretch of 3. That's the function for that graph there. Here we can see that from the origin we have to go right 3 spaces, right 1, 2, 3. Inside our absolute value, since we went right 3, it's x -3. It is reflected over the x-axis. It's pointed down, so we know that we should have a negative in front of our graph. Now let's check our slope, if you will. Let me go down 1, right 1, down 1, right. Okay, good. So we don't need any number in front of the absolute value, but we do need that negative since it's flipped. Okay, example 16. From the origin, looks like I'd have to go left 1, down 2 to get to the vertex. I had to go left 1, down 2. So inside our absolute value, we want x +1, and then to the right, do -2. Now we can tell that we have some sort of compression or shrink going on here. Let's figure out what it is. I have a perfect coordinate at the vertex and another one there. So rise over run. Up 1, right 3, up 1, right 3. So we need a 1/3 in front of the absolute value. And now this one, y equals, let's see what is our vertex. You have to go right 2, down 1. Right 2, down 1. Let me check the slope while I'm here. Down 1, right 1, down 1, right. Okay, so no stretch, no shrink, but it is reflected over the x-axis, so put a negative in front. That first number is +2, so inside the absolute value, do x -2. And to the right of the absolute value, -1. Okay, now we're going to graph some absolute value inequalities. Notice that this graph from the origin is going to shift left 2 and then down 4. That's our vertex. So from the origin, left 2, down 1, 2, 3, 4. That's where our graph is going to begin. Now let's figure out where we're going to plot all of our other dots. Look in front of the absolute value. You see a 3. We're going to use that to plot the rest of our dots. Think of it as 3 over 1. So from the vertex, you're going to go up 3, right 1, up 3, right 1. Go back to the vertex, go up 3, left 1. Now this is an inequality, so we're either going to connect these dots or we're not going to connect them, or we're going to dash them. I'm just going to leave them as dots. I'm not even going to fill them in because this is not an equal to statement. There's no line underneath the inequality. So I'm going to leave it just like that. Now we do have to do some shading. This is a greater than symbol, greater than. All the values where y is increasing is that direction. So we want to shade everything that's going to be in this zone here. Test point, you could put anything, any ordered pair that is in your purple zone here. So you could go left 1, up 2, left 1, up 2, And that would be a solution to this particular set of inequalities. Yeah. All right, over here. Inside the absolute value, just an x. To the right of the absolute value, minus 4. This is where we're going to begin our graph. So from the origin, go down 1, 2, 3, 4. Look in front of the absolute value, 1 over 2. That's going to help us plot the rest of our dots. So from the vertex, go up 1, right 2. Back to the vertex, up 1, left 2. Now, do we connect these? Do we leave them as dots? Look at the inequality. This is a equal to statement. So we're going to need to connect these dots. Now for our shading, this is a less than, and all the values where y is becoming lesser, decreasing, are this direction. So you'd want to shade down here. Don't worry about the test points. I mean, if you don't get it, then talk to me. I'll explain it. All right, so let's start with our vertex here. Looks like we're going left 4 from the origin. Left 4, and then down 1. So start at the origin, left 4, down 1. Look in front of the absolute value. I don't see any number. I don't see a negative. So what we're going to do is from the vertex, go up 1, right 1, up 1, right 1, up 1, right 1. And then back to the vertex, up 1, left 1. Since this is a equal to statement, there's a line underneath this inequality. Let's connect the dots. This is a less than, and all the values where y is decreasing is this direction. So we want to shade below that line that we just connected. And then last one, let's start with our vertex. Looking inside the absolute value, all I see is an x. Looking to the right of the absolute value, there's a 6. That's where our graph is going to begin. From the origin, go up 1, 2, 3, 4, 5, 6. Now, where are we going to plot the rest of our dots? Look in front of the absolute value, there's a negative. So think negative 1, down 1, right 1, down 1, right, down 1, right. And then back to the vertex, down 1, left 1. Do we need to connect these dots? No, not an equal to statement. So just leave them like that if you want to. And for our shading, this is a greater than, and all the values where y is getting bigger is that way. So we want to shade above those dots. Good job, Algebra 2.